This video's topic is molecular representation. And before I start talking about the rest of chapter 1, I would like to discuss this topic from chapter 2. In this topic, we'll learn about different styles of drawing organic molecules, basically learning the language of organic chemistry. And I believe it's necessary to learn it before we dive deeper into other topics in this course. Chemists use many different styles to draw molecules. Let's consider the structure of isopropanol with the formula of C3H8O. The very first structure is the Lewis structure. We just reviewed how to draw Lewis structure. So in the Lewis structure, we draw all the atoms and all the bonds, as you can see here. In the partially condensed structure, we don't do that. So if you look at the Lewis structure, we have a carbon here, 3 hydrogens attached to it. In the partially condensed structure, instead of drawing this part, we just write CH3. Similar to this side, we just write CH3. So whenever you have a carbon attached to 3 hydrogens, you can write that as CH3 in partially condensed structure. In the third structure, which is fully condensed structure, we don't show bonds. And sometimes this is a little bit tricky especially if you have larger molecule, it's not that easy to come up with the structure. So the very first thing to consider in the condensed structure is presence of parentheses. So when we have parentheses, the number beside that parentheses shows the number of groups in the parentheses. So inside the parentheses, I have CH3 multiplied by 2, meaning that I have 2 CH3s. Another important thing here is whatever is the atom beside the parentheses, these groups are connected to that. So if you look at the partially condensed structure, we have 2 CH3s connected to the carbon. We have 2 CH3s connected to the carbon. This carbon connected to the hydrogen. Similar here, hydrogen. And then it is connected to the OH. You can see the OH. These are 3 different ways of drawing organic molecules. However, they are not the most efficient ways. Especially if you have larger molecule, it's going to be sometimes very time consuming to draw the Lewis structure, and sometimes very confusing if you just draw the condensed structure. So organic chemists came up with the idea to draw the structure in another way, and we call that bond line structure. Here you can see the bond line structure of isopropanol. We have 2 CH3s here, a CH here, and OH here. To understand it better, let's see how we can start from the Lewis structure and get to the bond line structure for isopropanol. The first step to draw bond line structure is to remove all the carbons in that bond line structure. So organic molecules, they have a lot of carbons. We just remove them, so it makes our life easier. If you look at isopropanol, we have 3 carbons in isopropanol, and we remove all 3. The second step is to remove all the hydrogens that are bonded to carbons. So hydrogens. Alright, so right here, this carbon has 3 hydrogens attached to it. We remove our 3 and we don't show them here. This carbon has 1 hydrogen attached to it. We remove that one. The third carbon also has 3 hydrogens attached to it. We remove all 3. The second carbon, as you can see, it has oxygen attached to it and there is a hydrogen attached to oxygen, we keep the hydrogens that are connected to heteroatoms. And heteroatoms are atoms other than carbon and hydrogen atoms. So we show the heteroatom and also the hydrogen attached to it. This is the final bond line structure for isopropanol. Again, as a review, remember that each endpoint and corner has a carbon, and we know that carbon can make neutral carbon can make 4 bonds in the molecules. This carbon has 1 bond here, the rest are hydrogens and we don't show them. Same here, this carbon has 1, 2, 3 bonds attached to it. The last one is hydrogen and we don't show that hydrogen. The bond line structure of alkanes and alkenes are always drawn in the zigzag format. So if you look at here, the first structure is an alkane. It has all the carbons connected to each other with a single bond. And the second structure is an alkene. You can see a double bond between carbon 1 and 2 and carbon 3 and 4. The reasoning behind that is because all the molecules are in 3D. On a paper, we cannot show the 3D structure of the molecules, but we can do our best. And the best way to show the basically a structure of the molecules in alkanes and alkene is the zigzag format. However, if you have an alkyne, which is carbon-carbon triple bond, they are always linear. To make these points clear, I made a video of the model. Watch the video for more explanation. Okay, so this is the 3D model of alkene. The second molecule that you can see, I drawn that here. This is carbon number 1, carbon number 2, 3, 4, and 5. As you can see, there is a double bond between carbon 1 and 2 and carbon 3 and 4. So as you can see, the 3D model shows that the alkene is in a zigzag format, and that's the reason we draw that in a zigzag format on a paper as well, to resemble the actual model as much as we can. Now if you make the model of the third molecule, just pay attention that I didn't attach the hydrogens in this model to make it easier to see the linear and zigzag part. So this molecule, this is carbon number 1, 2, 3, 4, and 5. So this part of the molecule, it's an alkane, so it's in a zigzag format. However, this part of the molecule, we have carbon-carbon triple bond. It's an alkyne, so it's in a linear format. While drawing this structure on a paper, we should follow this model. So we never draw the alkyne in a zigzag format. It's always linear. Another important thing is this carbon right here. Sometimes when you draw the structure on a paper, there is a chance that you miss this carbon. Just pay attention that there is a carbon here connected to this one with triple bond. So if you compare these two models, if you compare the triple bond to the double bond, you can see the model also shows the triple bond is shorter than double bond, and of course it's stronger. So these are the model. Hopefully you guys buy your molecular kit, you can make the model of your molecules, and which makes it easier for you guys to visualize the actual structure of the molecule in the 3D format. Okay, so to draw the structure of third molecule, let's first number all the carbon. This is carbon 1, 2, 3, 4, and 5. So carbon 1, 2, and 3, they are in a zigzag format. Then we have carbon 4. There is a triple bond between carbon 4 and 5. So if I number these carbon 1, 2, 3, 4, and 5, this carbon right here, it's not in an actual corner and it's not in an endpoint. So there is a chance that you miss this carbon. Just pay attention that here there is our carbon, so don't miss it. Don't miss this carbon. Alright, so in the bond line structures, you should always show the formal charges. You don't have to show the lone pairs. You can if you want, but all the formal charges must be shown. So in the first structure, if I ask you how many lone pairs are on nitrogen, so you can do a very simple math here. If you remember the formula of formal charge, it was number of valence electrons minus number of bonds minus number of dots or electrons in lone pair. So it's just a very simple math here. The formal charge on nitrogen is -1. Nitrogen is in group 5, so it has 5 valence electrons. Nitrogen has 2 bonds connected to that. And to find the number of lone pairs, we just need to solve this equation. And if we do that, the number of dots, or the number of basically single electrons, is gonna be 4. And the question was how many number of lone pairs. We know that in each pair of electrons we have 2 electrons, so it's gonna be 2 lone pairs on the nitrogen. So this nitrogen has 2 lone pairs on it. This is one way of doing that. However, the second way, if you remember from the previous video, nitrogen usually makes 3 bonds, but we can have divalent nitrogen as well. Nitrogen with 2 bonds always is negatively charged, and it has 2 lone pairs. Now in the second structure, let's see how many lone pairs are on oxygen. So if you do the math, it's number of valence electron minus bonds minus dots. The formal charge is +1. Oxygen is in group 6, 6 valence electrons. And number of bonds, you can see 3 bonds there minus number of dots. If you do the math, the answer would be 2. So it has a 1 lone pair. And again, this one, if you remember from the Lewis structure video, oxygen is usually divalent. However, oxygen with 3 bonds, tetravalent and trivalent oxygen, is always positively charged, and it has a lone pair of electrons on it. Now, for carbon, let's answer the question below. So the question is asking, which of the carbons below are missing a needed formal charge? So the first one is carbocation. Carbon with 3 bonds, trivalent carbon, without any lone pairs, without any electrons around it, is always positively charged. You can even do the math to find the formal charge here. You need to, carbon has 4 valence electrons minus number of bonds, no dots. That gives you formal charge of +1. Carbon radical Again, carbon has 4 valence electrons, it has 3 bonds, and it has 1 dot. So the 4 mole charge here would be 0. Carbon radical is always neutral. And carbon anion, so carbon, it has 4 mole charge of 4 minus 3 bonds minus 2 dots. The 4 mole charge would be -1. Carbon anion or carbanion is always negatively charged, -1 charge. Alright, so to practice, the question is asking, draw the following structure in the bond line format. The first structure is the structure of vitamin C. I suggest you, before drawing the bond line, before attempting to do that, let's start numbering all the carbons. So I call that carbon number 1, carbon number 2, 3, 4, 5, 6. And the reason for that is to keep track of your carbons and don't miss any of them. Also, you can see which atoms is connected to that specific carbon, so you don't mess up with your final structure. I start with oxygen. Oxygen is connected to carbon 1. You remember in the bond line structure we don't draw the carbon. And then carbon 1 is connected to carbon 2. I don't draw carbon 2 as well. 2 to 3. 2 to 3, it also has a double bond. Then 3 to 4. And then 4 to oxygen. Also carbon 4 is attached to carbon number 5 and attached to carbon number 6. Alright? So we have drawn all the carbons. Now, to carbon number 1, we have double bonded oxygen. And if you remember, in the bond line structure, we draw all the heteroatoms. Carbon number 2, this is carbon number 1, carbon number 2, number 3, 4, 5, and 6. Carbon number 2 is attached to the oxygen, and that oxygen also attached to the hydrogen. And if you remember, we show all the hydrogens attached to the heteroatoms. Carbon number 3 also attached to the OH group. Carbon number 4, it is attached to oxygen, attached to the hydrogen. We don't show that hydrogen, and it is also attached to another carbon. So that one is good. Carbon number 5, it is attached to the hydrogen. We don't show that one. Hydrogens attached to the carbon are not shown. And it is attached to the OH group, so we show that one. OH. Carbon number 6, it is connected to 2 hydrogens. We don't show them. However, it is connected to the OH group, and we show that one. Alright? So this is the bond line structure of vitamin C. Pretty easy. Now, in the second structure, which is a condensed formula. Condensed formula can get tricky, especially if there is parentheses, as I said before. So to start with, just know that this parentheses, it has number 2 beside it. That means I have 2 of these groups attached to this carbon. Whatever is the atom after the parentheses, these groups are attached to that one. So I just put a dot for that carbon. I would like to number them, all of them, this carbon, and this is just 2 carbons. So this is my carbon number 1, and to that carbon number 1 I have CH2 CH3 group attached. CH2 CH3 group attached. CH2 CH3 group is ethyl group in organic chemistry, and I have 2 of that connected to carbon number 1. So see, CH3 CH2 carbon number 1, CH3 CH2 carbon number 1, and then carbon number 1 attached to the hydrogen. We don't show that hydrogen, and then attached to carbon number 2. So this is my carbon number 2, and then carbon number 2 attached to 2 hydrogens. We don't show them, and also attached to the nitrogen. We show heteroatoms, and also nitrogen is attached to 2 hydrogens. We show all the hydrogens attached to heteroatoms. Okay, in the third structure, so again I would like to number my carbon. This is 1, 2, 3, 4, 5, and 6. So carbon number 1, I start with a dot. It is attached to carbon number 2. This is 1. This is 2. Carbon number 2 is attached to carbon number 6. Carbon number 2 is also attached to carbon number 3. This is carbon number 3. 3 is attached to 4. And 4 is attached to 5. Alright? So all of these carbons have hydrogens attached to them, and we don't show the hydrogens. However, remember that we have a charge on carbon number 2, and we need to show that charge. This is the bond line structure for these carbocation. Alright, so sometimes the question may ask you about the molecular formula. So you have the bond line structure and the question is asking for molecular formula. To answer this type of questions, what I suggest you to do is to draw all the hydrogens connected to the carbons. So we know that each corner and endpoint is a carbon. You don't have to draw them, but I suggest you to draw all the hydrogens to prevent confusion. So I start with the first structure. This structure is a bicyclic structure. We are going to learn about them later on. But to find the molecular formula here, I start with this carbon. So this carbon, it has 1, 2, 3 bonds. So remember, there is no charge on this molecule. That means that all the carbons are neutral. Therefore, neutral carbon has 4 bonds. And another important thing is never give carbons more than 4 bonds. Carbon cannot take more than 4 bonds. It can have less, but it cannot get more than 4 bonds. So this carbon right here, it has 1, 2, 3 bonds. Therefore, there is 1 hydrogen here attached to it. This carbon, it has 1, 2, 3 bonds. Therefore, the 4th bond is a hydrogen. This carbon, it has 1, 2, 3 bonds. The 4th one is hydrogen. This carbon, it's a corner, so that means it's a carbon here. It has 1, 2 bonds attached to it. So we are gonna have 2 hydrogens here. This carbon, it has 1, 2 bonds. Again, it's a corner, so we have carbon there. So 2 should be hydrogen. This carbon, it's also a corner, has 1, 2 bonds attached to it. So the other 2 are hydrogens. And this carbon right here, it is again a corner. It has 1, 2, 3 bonds attached to it. So the 4th one is hydrogen. Now very easy. So number of hydrogens, number of carbons. Let's count. I have 1, 2, 3, 4, 5, 6, 7 carbons. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So the formula for this one is C7H10. Now, for aspirin, this is the structure of aspirin, bond line structure. Again, we start with drawing all the hydrogens. So the end point here, we know that end point is a carbon. It already has 1 bond. So the other 3 must be hydrogens. Then we move forward. This is a corner. That corner has a carbon. It has 1, 2, 3, 4 bonds. So it is good. I'm not giving more hydrogens. Carbon cannot take more than 4 bonds. Then oxygen. This oxygen is good. Then we have another carbon here. So this carbon has 1, 2, 3, 4 bonds. This carbon is also good. This carbon, it has 1, 2, 3 bonds. So 1 hydrogen here. It is similar to this carbon, similar to that carbon, and similar to this carbon. So this carbon, there is a carbon here. It's the corner. It has 2 bonds, 3 and 4. So it's good. Now let's count. We have hydrogens here. We have carbon and we have oxygen on this molecule. So let's count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. Number of carbon, remember end point and corners. We have carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And oxygens, we have 1, 2, 3, 4 oxygens. So the formula for this one is C9H8O4.